myriad of them, right? There are many, many of them. Which one does what and what one works best is kind of one of those things you have to learn by example. You have to do it and have to see whether or not this particular is going to work, etc. I would say, in a certain extent, there is an art and a science to neural networks. The science is the math, right? And the art is just getting used to what's worked in the past, seeing whether or not this general shape kind of conforms as a network, conforms to solving that particular type of problem. We could think of it in this way: if the internal morphology of the network, how many nodes there are, and how deep the system is, work well for one problem, then it's a potential that any adjacent problem, at least within the sort of problem space that we might have described as having the same relative characteristics or the same goal, might be similar in terms of their functionality. So we say that if we have one network that works good for this task, then it should work well for any task that is similar to it. We'll take that and we'll characterize that with regard to hyperparameter optimization, and also the idea of fine-tuning networks, right? Through the process of taking an existing network and then making it work well or better for a specific subset of tasks. I mentioned the idea of the, I think we talked about the representational power and the universal approximator theorem, right? We mentioned this, I think it was class before last or so, maybe it was last class, I'm not sure. But I've mentioned this to you along the way, but I haven't talked to you about this one. All right, the no free lunch theorem. This one's kind of interesting because we say that a classification model for supervised learning are actually vast oversimplifications of reality. Because no matter the complexity of the data set, that particular informational representation is a dimensionality reduced version of it. You can think about it in this way. If you've ever heard of Plato's allegory of the cave, right? We see the natural world is projected through sort of the keyhole of the cave entrance, and we ourselves are sitting looking at the projection, the shadow puppetry, right on the wall. If I take my generalization from the image that is projected on the screen currently, how many fingers do I have?
One.
Right? One, right? But how many do I have now?
5.
Right? The relationship and the projection of the data change depending on the access, depending on the way in which that information is incorporated and distinguished. So when I'm talking about this and saying it is an oversimplification, it is often because we have dimensionally flattened that information, or temporally flattened it would be probably one of the things that's most common. What's one of the first things we usually get rid of whenever we think about the concept of training some kind of system? Well, I don't care when I collected the sample, right? Most of the time you could get away with that. You could say it doesn't matter whether the sample was collected at noon or midnight, it's still of the same thing. And let's say that if elimination conditions aren't dependent, then that sample should maintain relatively the same representational power, right? It still shows that thing within the frame of reference. But if you have an operation, let's say something like a flower that opens during the day and closes at night, then I would have a totally different perspective on what I was looking at, depending on looking at it noon versus looking at it midnight. Right? Even if all the other characteristics are at play, you have a process that changes relative to time. So the dimensionality flattening of treating all times as the same relative significance is an oversimplification that may cause problems for us in the future process. So the simplification relies on an assumption. An assumption. I have to make a causal inference link between those elements related in the system. Whenever that assumption fails, all right, what's the problem? The problem is that that network or that system or that model goes from high utility to virtually useless. So when I say assumption, I'm talking about the degree to which the model has utility. Model serves the purpose of what? Predicting the future. It takes information about some previous sequence of events, a data set, and then tries to create a trend map or some sort of extrapolation capacity, and whatever level of dismissal of those little key elements, right, What often do we do whenever we create experiments? We control them. We place them in controlled environments. So whenever we place them in controlled environments, what happens? We have eliminated the true complexity that can happen in the natural world. Similarly with networks or with models in general, we often treat them as if they're happening kind of in this vacuum, this hypothetical space on a computer. But then they get released into the wild, and what happens? The generalization starts to fail because they were only tested within the confined space of the controlled environment. So attempting to control can be an assumption that can cause a system to drop. One of the interesting aspects of this is that the generalizability of a model correlates most with a reduction in overall accuracy. Guys, those of you who are in ISL remember the argument about the bias variance dilemma, right? Everybody know the bias variance dilemma?
Yes.
Everybody?
Yes.
Okay, anybody that doesn't? Raise hands. Okay, good, awesome. I'm glad everybody's on the same page. This allows me to skip a couple of things. What I'm making an argument for here is that there is no model that is capable of fully satisfying the bias variance dilemma, because the more highly accurate, the better at solving that specific type of problem, what happens? The less generalizable it becomes. The more specific assumptions the model must make in order to be able to assume or to inference the actual outcome of that predictive framework. So the more specialist you are, the less generalizable, right? It seems obvious.
Yeah.
Those words are in fact the opposite of one another in our space. So why is it that we naturally assume that a system could be able to inherit the relationship of being a model that could solve any problem? According to our current understanding of all modeling methodologies and techniques, there is no such thing as a model that solves all problems. As such, there is also no neural network which can be described to solve all problems. Thus, I must include the caveat that there exists some function, yes, that solves that problem relative to that data set for some error greater than 0. This means that the error will always be non-zero, not necessarily just because of the process variability characteristics of the data collection, right? But because of those assumptions, those dimensionality flattening features that were left out, the domain-specific allocations that we took whenever we were collecting that space. We can't collect every single feature of the natural world, so our data sets will always be biased by the initial assumptions that started that data set collection. What's one of the problems with collecting medical data? Where do you collect most of your medical data from?
Electronic health record.
Okay, but where are the electronic health records collected? Where do you go?
Hospitals.
The hospital.
The clinics. Anywhere.
Where do people that are at the hospital for, right? I am really healthy today. I think I'm going to go to the hospital. Get my health record updated, right? Get the ground truth so I know when I'm sick, what happens, right? No, we don't do this. It's really weird, right? So we make huge data sets of people that are sick. They compare sick people to other sick people. Okay, this is one of those things that, like, when I first started to think about it, I'm like, wow, that really is stupid. And then later on, I was like, but how else do you do it?
Yeah.
I don't know. You got me, right? This is the reason why I don't solve problems. I'm just the idea guy, okay? I don't do busy work. When we're looking at this, I want you to really understand that it is going to be massaging. It is going to be very carefully balancing the degree to which we want to try to refine and highly specific outputs of the system that is going to be important here. And the metrics we utilize to do so, what's the first metric we utilize to do so with regard to linear regressions? Everybody remember linear regressions? Change the slope of the function until what? The absolute square error goes to 0, or goes to the min function, right? So then the model overfits, right? We give it some more parameters and the model overfits, and what do? We say bad model, right? And the model says, I was just doing what you told me. You said minimize the function, right? You said minimize with respect to this dimensionality. And then we go, no, but you overfit. And it says, no, I did exactly what you told me to. So what do we have to do? We have to add new penalties. We have to have ways to be able to control it. We have to put in restrictions for the way that both the model performs and the way it trains in order to be able to optimize the pursuit of that model training process. So keeping in mind that our models can create and can reduce to reasonable subsets of minimal complexity, we're going to preserve that as much as possible. I'm going to go ahead and skip past this slide because this one's pretty simple, straightforward. This is a control systems diagram of a neural network, right? We've seen many things like this in terms of our previous programming models. The change in the output is controlled by an update process, right? A change of parameters operation. This is the thing that we really would like to know the most about. How do those parameters change, okay? Well, we're going to talk about the idea of a gradient surface. And this is the first time that we're going to introduce the mathematical framework. Now I'm going to walk over to my other slides real quick, and we're going to look at the ones that were presented for this process, okay? So we're going to go over to the slides that are using Goodfellow data, right? Remember, we're used to this concept of information and feature extraction. Where do we get the data that we're utilizing to make the assessments about the model? We're dealing with it from some data set that has already been labeled with the important characteristic of the target, and then we're going to select the features about it based upon the information that is at play. Okay? So the feature extraction process of something like a classification model would work by doing what? Prediction of whether or not something is a family car in this case. Okay? So we said here, we say class C is that of family car. Prediction of the output of the system is that particular car a family car. So what do I mean by family car, right? I'm talking about something that can hold at least 5 people, has good crash safety ratings. It doesn't probably get the world's best gas mileage because it's heavier. Probably something like a minivan or a sedan, right? Something along those lines. We're used to what we say, so the soccer mom, soccer mom mobile, right? Everybody's used to knows what that is, okay? So when we say that knowledge extraction comes from where? That comes from what we expect from the family car. What features did we predict for it? The outputs of the system are just going to be positive and negative quantifications. So if this is the end state process, we've included both what we want the model to do, what the model is going to make its decisions based upon, and what the targets of that system are going to be. We're then going to have some representation here which is going to say perhaps that price and engine power characteristic. The training set of this system is going to be related to the core data that's available within the entire learning space. So I like to say this, that data sets, the separation between training and testing data is important, not simply because of the fact that we have to have some data held back, but because the amount of data we have, as well as the amount necessary to make a reasonable assumption based upon it, will be very critical to the scale of the network. When we worry about overfitting in neural networks, it's very different than whenever we worried about overfitting within standard linear systems, because oftentimes the neural networks can have many, many more parameters, thus more flexibility when it comes to their capacity to fit to specific data points. So whenever I'm trying to construct a model, I'm going to have to make sure that I have adequate samples to train it, right? I have to have enough samples that are going to stop the system from effectively overfitting relative to the number of examples that I have. Also, take into consideration here that we have a feature vector that contains 2 input elements, right? A feature that's 2 input elements to a binary output. Very simple. This is just a spatial classification. Now we have class C, which is some subset of the characteristics in play here, describing 2 thresholds of the activation output, an upper and a lower band. So we've created a sub-region based upon utilizing 4 lines, right? I needed 4 lines to cut up this segment of the data. Above this point or below this point, right? Above this point or below this point. We're still making our classifications based upon what? Strict thresholding parameters for both of the input features. So we wanted to try to make something a little bit more generalized. We'd have to create a higher dimensionality classifier. We'd have to allow the system to have more flexibility. Right now it has 4 tunable parameters, which are just thresholding characteristics. Do I need anything, do I have any slopes involved with those elements at play?
No.
No, they're not slope elements, they're just thresholds based upon singular features. So the regression process is going to involve, right, the exhaustive process of attempting to reduce total error based upon the expected value for some function g of x relative to the data points within the system. This is for those of us who remember multivariate regression, right? Whenever we're looking at something that is a higher order function, we say that there's a higher order function. It's going to be composed of, for the first order elements, which is just the slope characteristic, and we're going to ask ourselves, is that sufficient to be able to create this distinction, right? We look at this earlier on and we say, does this solve the problem? Yes, it does solve the problem. But at the same time, how likely is it going to be to solve new problems, right? Are all the samples that are going to be in the positive case going to be enclosed perfectly by that shape? Probably not. So what are we going to need? We're going to need to take a little bit more information from the data set and determine some characteristics of the distribution. What don't we want to do? We don't want to overlearn exactly just the area that is present or is occupied by the positive samples, right? We don't want it to be just a line just enclosing just the minimal space of the union of all those points, because why? That's an overfit in the same way that this is probably a little bit of an underfitting, right? This likely underfits because it doesn't highly generalize. And it might actually take into consideration too much of the space for positive samples, because we notice over there, right up against the very edge of that top segment of that square is one of our first negative examples. Have we really split the difference between the negative and the positive samples to try to optimize the likelihood of the inclusion or exclusion of a specific vehicle within the set? No, no. This is the most reductive version of classification. This is the most basic way in which we could create a classification metric. Notice, do I have any factor of price when making a consideration for engine power? No. Those two modeling paradigms are handled completely separately. There is no overlap between them. So what I've done is effectively projected the data in 2 different axes, and I've taken upper and lower thresholds relative to some value within the system. Where those particular values are established from, I can't tell within this slide. Right? What was the picking criteria? Why did I decide that this was the best box that I could draw around the outside of them? We instinctively know by looking at it, those of us who have done some data science, that this looks sus, right? Say, yeah, no, I don't feel it, okay? It looks really, really overly boxy in comparison to what we might do. But for something like just a strict tree system, strict trees might provide something like this for us. Now, do I think that they're going to be a little bit more explanatory as the reason why they tried to pick those boundaries? Absolutely. Do I think that it's likely that it's going to throw a boundary that close to a negative sample? Probably not. Probably not. What's one of the problems with this particular data? We're not comparing, we don't have any testing data, right? This is just the training and performance. We don't have testing data to compare this to. So without testing data, we have no idea whether or not this particular model is actually holding up to any degree of scrutiny for future operations. So we're going to have some additional metric to determine both whether or not the parameters are sufficient to solve the problem, as well as to determine whether or not it's robust, it has future operability. So keep in mind that the training, I do this sometimes, I do taining and trusting, I don't know what happens to it, but training and testing separation is effectively more informative within the neural network space than it is in some of the other more traditional machine learning spaces, because we select the numbers of the elements of the network based upon some characteristics of that parameter space. So notice here I've got a weight characteristic, right? I've got a square operation of one of the input features, and then I have a weight, and I have the first order operation, and then I have some weight naught, W naught in this case. What does that look like to us? That's just a simple second order relationship of this particular expression. Over there on the left-hand side, I have some relationship that says that the error estimation or the error metric, right, would come from or could come from the relationship between the output of this system, right, the output real R relative to G of X of t, right, the transpose of that output matrix for the square. What does this look like to us? We have a summation, we have a number, we have a difference of square operation.
Mean squared error.
Mean squared error, that's MSE, okay? Should know it anywhere. It's at this point in time, right? We've pounded, everybody's had it pounded into their heads to see that that one looks fine. How do I determine what values are going to be utilized for the weights in that system? I just min the output of that function over there, right? I min E for G given X. So the system is going to iteratively loop through all the sample values, trying and failing to be able to return that output value. But which direction do I go with that weight in which case, right? Do I add more W? So W's W2 there, right? That's the weight that would be applied to the square of the first element of the regression, right? So how do I change W2 and how do I change W1? What's the update process for it? Do I just randomly start selecting values? Does anybody have any idea how we go about that? I put it in the algorithm, right? And it just does the thing.
Yeah.
Yeah.
Yeah. Okay, we're going to talk about that. We have to talk about that. Okay? Data set partitions, we'll deal with this later on. We talked about the idea of training, complexity simulation, probabilistic classification. Okay? Let's first talk about the idea of Bayes' rule with conjunction of this output. How does Bayes' rule apply to this? Okay, past information allows us to make inferences for future information, right? Everybody's done Bayes, anybody not done Bayes? At some level. Okay, good, I'm glad. Makes it easier for me. If somebody's not here, this hasn't done Bayes, plenty of resources for that for them, but at the same time, I like to say that this is a pretty primitive construct within machine learning. Why does this matter with respect to the idea of how we would update the weights? Every time I try a new value, what am I doing? I'm creating a data set, right, relative to the performance of those sets of weights or that regression operation. And I'm going to be able to give you something based upon the likelihood of the model to converge to the minimal value based upon the previous sequence of values. So as I train the model, right, if I have two knobs, these are the coefficients, and I adjust those two knobs, right, I can adjust one independent of the other one, see how much it changed, this one independent of the other one, see how much it changes, and try to minimize each one, right, to try to keep what's the min relative to each of those values. At each step of the process, as I'm changing and moving through each of those values, I'm effectively adding to the prior. That is the information that I have already done. The posterior, right, the prediction of likely outcome in this particular case, this is just simple inclusion or exclusion, right? But I can make this, I can reduce this to saying, what is the likelihood that this set of weights or this set of coefficients will have an error less than the previous example, less than the previous system. I can use Bayes' theorem to be able to do that calculation, right? I can say the likelihood based upon the information that I've collected. Now, would that be very much a sledgehammer approach? For sure, because we have other tools that we can utilize to create closed form solutions for the system. But the key item here is that the inference about what is likely to happen will come from evidence. What evidence do we have? Well, we knew what the parameters were at the previous step, right? And we knew what the performance was at that step. So we're actually going to try to create a sort of meta-analytical perspective on what needs to happen to the weights in order such that when the weights are multiplied by the coefficients, the new version of the function is lower than the previous one, right? And it's going to be based upon the previous level of performance and the previous state of the system. All right, I'm not going to worry about this, but we talk about this with respect to the idea that loss and risk are associated. Loss and risk are the primary metrics by which we utilize to produce an improved understanding of the model. Loss is what? Loss is when we do not get the classification output we're looking for, or the regression output we're looking for, as a result of the difference between the declared state class and the relative class. So you could say, if I did something, this example that I think we talked about previously is a loan. I give a loan to somebody, I'm from a bank, and that loan does not get repaid, right? I have two options. Either they're going to repay it or they're not going to repay it. If I misclassify that specific individual, what happens? I lose money. So the metric would then be the quality of my model relative to whether or not I should issue a loan to that individual. The metric that I'm going to utilize in that case is the total loss. How many inaccurate operational classifications did I provide? Risk is a similar assessment in the effect that it implies that there are different types of loss. Some types of loss are different than others, all right? Some of you may remember this story if you've heard it beforehand, but I like to say that this is a good analogy of risk assessment. You have a flight going over to some nation, right, of humanitarian aid. On that flight, you have two containers. One has apples and the other one has grenades, right? At some point in time, the flight gets a little bumpy and the containers fall over, and on the floor, all the apples and the grenades mix together, right? The apples are those little green ones, right? Granny Smiths, right? It's kind of dark on the plane, and so everybody's trying to set the containers back up, and they're just picking stuff up off the floor and putting it in the container. So at the end of the day, you unload the containers off onto the ground, and you have children coming by to get their apples, right? Their humanitarian food aid. You have the soldiers coming through to get the grenades and munitions to fight their war. There are two different types of loss here, right? There's two different binary operations. What each of the targets was intended to do is different, and so the results are different. What happens whenever the apple is misclassified as a grenade? That means it goes over here. The apple has been put in the grenade bin. That means that the soldier's coming through, grenade, 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 apple. Okay? And the soldier goes, if I throw this at the enemy, I'm just going to be giving them free food. Okay, right? We don't want to aid the enemy. Okay? So instead of getting the munition, they get a tasty snack. Not a big deal. Let's go over to the other end of the tray, right? Let's go over to the other end of the system. You have children walking through. Oh, yeah, exactly. Oh, no. Oh, no. Okay, what was the problem over here? Okay, instead of the guy getting the grenade, which is probably not really a defensive weapon anyway, it's probably relatively aggressive, but the idea is saying he's not able to defend himself, instead he gets snapped. Yeah. What on the other side, what happens? Apple, 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 grenade. Okay?
Yikes.
Not good. Not good. So when we talk about risk, right, we're talking about the relative cost of a system can change based upon what are the inherent qualitative characteristics of the outcome. If one outcome is considered to be systematically or operatively significantly worse than another outcome, we might choose to err on the side of caution and put more of the apples in the grenade bin rather than putting any possible grenade in the apple bin, right? So we would do what? We would move our threshold of where we might identify the difference between apple and grenade over pretty far so that it moves farther over into the apples whenever we're making the distinction between which class grouping we're dealing with. So when we're talking about the metrics by which we utilize to minimize the system, it's not as simple as just looking at whether or not we're minimizing the total distance away from the linear element of the system. We're going to have to utilize different error and risk and associated loss and risk metrics based upon the use case of the model space. All right, we've already talked about discriminant functions. Two class operations, yes. So yeah, for maximum likelihood and discriminant operations. Okay, so let me go back to my other slides real quick because we're actually on. Okay. Okay. I know I'm popping back and forth between slides. There's stuff on both of these that we need because we're dealing with classification a little earlier on, than I typically do whenever I'm discussing neural networks. And as I told you beforehand, it's my first time offering this version of the class, because in the past, neural networks has just been its own thing, but we're trying to condense the neural network segment up a little bit so that we can do a little bit more time on talking about some of those deep learning operations. So the metric by which we're going to utilize our understanding of the reduction in total error of the system is going to take advantage of or utilize a gradient surface optimization type problem. So many of you have already seen this slide before, but I think that I'm going to try to go into it a little bit more detail, and we're going to talk about a little bit of how this calculation happens. All right? Does anybody remember doing gradients in calc? What gradients represent? Okay, you do remember? Okay. Let me go ahead and show you something, because I have a web link for what I think is a really pretty good example here. If I can get it to play. Okay. If I were to represent the gradient surface for a two-dimensional model, what I would do is I would go from that traditional little bowl shape, right? That's the side view of this system, this parabolic shape. Now, what this is indicating is that the relative parameterization for each of these elements is roughly the same. So I could adjust some of the characteristics of the system to describe the relationship of the gradient calculation based upon the rough value for the local estimate. So what is the gradient of this surface? Why did I switch into geometry and starting to do all this geometric analysis? Well, if I go back to this previous slide, and we look at the relationship of the neural network, right? We say that the weights down here, W, okay? We said earlier that we could describe the relationships between the nodes of the network as W, weights. That's the emphasis or the rate of change assumed by that connectivity. I start off with some parameter W naught in that initial configuration. That's the first step. That's my first guess. This is one of the things that I have to tell you is that when we make a neural network, the first step of the process is to seed random data points into all of the available parameters. Right? We usually use what is called zero mean Gaussian. All right? Everybody remember that? That's a zero mean distribution, normal distribution. So normal centered around 0. We use that type of noising to effectively randomly select values out of that zero mean distribution and assign them to the weights. This is a bit like if you were looking for somebody in the woods and you took an airplane up, right, and you put all of your search party with parachutes, right, and as you're flying over the segment of the area in which you're trying to find the person, you just say, just jump out wherever, okay? You're good, okay? So everybody just kind of jumps out, and then as you're going along, you see this line of parachutes, and they're just sort of spread all over the space, just sort of randomly seated in. Why does this, how does this have any correlation to being able to minimize the error functionality? If everybody just sort of gets put in a random position, well, the argument is this. I could go very systematically through the forest, right? One line, turn around, one line, turn around. Or I could just say, okay, let's just start here, right? And work our way down whichever direction we're assuming we want to go. So let's imagine that the person that we're looking for had a radio. And that radio only worked whenever they were at a certain elevation so that they get a line of sight out to the tower. So our first assumption is that person's probably going to try to climb up to the highest position that they can go. So no matter where we start off with, no matter what the environment we start off with is, if I drop you in that position, and you don't necessarily know what that landscape looks like, what's your goal going to be?
Go north.
Climb a hill, all right? Climb a hill. So from wherever you're at, you're going to make a decision to always try to climb that hill because the assumed accuracy, which is correlated to what? That you are closer to the individual you're looking for, is going to be correlated with, or seems to be correlated with, the elevation that you can get to within your walking distance. So the idea here is that if this is the error surface, error should go down as your elevation goes up, right? The higher the elevation you are, the more likely you're going to be able to see that person. or find that person at that elevation. The relationship says as height goes up, right, for my search party person, then error goes down. So my initial assumption, I dropped you out of the plane, and then this is the surface area that you're interfacing with. The surface area says that you found a direction relative to this one-dimensional space, right, in which you can easily assume which direction was the surface or the direction of greatest increase, right? That you were easily able to tell where the slope went up. That seems like it should be a pretty good way to go about it, right? So if I was to say that the analysis of the surface relative to the greatest degree of change in direction would be something that we would call the gradient, right? It's the change in slope. The gradient will always point and is always calculated by the relationship between the current position on the surface, right, and any one given derivative, local derivative around the region, will calculate. It calculates all relevant adjacent derivatives as a result of only interfacing with the error surface in one position, right, a tangent interface. From this position, right, and the initial starting point, I am here, right? You are here. This is the mole map. I adjust the value of the weight based upon what? This is actually the first gradient. So at weight 0, the first gradient indicates that I need to move via the direction of greatest increase, okay? So when I say the greatest, the gradient, right, the direction of movement, I'm saying that weight is going to do what? Increase, right? Weight has to increase. What happens to the error as the weight increases? The error goes down, right?
Yep.
But if I keep going onto the other side of the system, I keep increasing the weight, increasing the rate, increasing the weight, what happens to the error again?
It increases.
I've increased again. I'm going to be trying to find some position, W star, which is the ideal configuration in which the relative degree of significance or the weight of that feature is correlated most directly with the quality of the output, right? It's the perfect mapping function between the input and the output. In a two-dimensional space, let's go back to the two-dimensional graphic, or I guess you'd say three-dimensional graphic. If I select any point on the surface, the error surface, right, now we're looking at it from the side, and I move sort of up and down that gradient, what happens to that vector that's being drawn off there to the side? And what is that vector? Well, the vector is the direction of movement that would indicate that if you moved in that way relative to this xy space, right? Relative to xy. If I moved in this direction, what is a vector made up of? It has a component of x and a component of y. So if I decompose this, I look at that angle and I say if I increase x by this amount, right? By this amount, and y by this, decrease y by this amount, I'm going to move in the direction of the greatest degree of increase of that function. The gradient always points in the direction of greatest increase of the surface that it's encountering and incorporating with. Relatively, we see that point, right? We see this point here on this shape, and it's interfacing with, it is a plane interfacing with that particular singular point on that error surface. The gradient is calculated by, as I said, going around all of the relative points around the outside of that current point A, right? That is the current value of the weights x and y. Now, what do I mean by weights x and y? Remember we said we had two weights in the previous system. We had W1 and W2. Let's just assume that the current values of the weight W1 is x, and the current value of the weight 2 is y. What are we looking at here? We're saying that if this is the error surface, meaning that this is the relationship between the rate of change of the weight of y, the significance of y, right? The rate of change of the slope of y, and the rate of this change of slope of x. Remember, earlier on I showed you it is a surface, right? The surface. It is a plane constructed here. This is the two-dimensional one. What does the three-dimensional, or excuse me, four-dimensional, five-dimensional one look like, right? Two-dimensional 3D. Starts to look pretty funky, right? Anything past 2D starts to get pretty complicated. So let's stick with just the 2D assessment. So if I wanted to try to find the ideal weights, the ideal amount to change x, and the ideal amount to change y, would I have to hold x static in order to change y, or can I change both of them at the same time in this case? I can change both of them at the same time, because I have a vector that shows me the direction of greatest increase in error. So what does that mean? If I go in the opposite of that direction, if I flip that vector around, that also tells me which way is the fastest way down the error gradient. Effectively, as I said previously, you have to look at this in both directions. You have to say that if your goal is to go up the hill, right, then your accuracy would be how far away you are from the top of the mountain. In this case, the proximity to the top of the mountain would be correlated with a decrease in relative error. So if your goal is to go up, then your error goes down as you increase. So they are inversely proportional to one another, right? They're inversely related. So since I don't know which direction is technically the best up in this particular case, I'm going to utilize a gradient, which is a localized assessment, to be able to change the value. Note here also the magnitude of this vector changes relative to the overall steepness of this surface as it gets towards the bottom segment. There isn't quite as much steepness going on. So our gradient is not going to be as high in magnitude for the vector. First order relationships of differentiation, right? So we say if I have one element of a network, f, that it relates to some other output in f, right? So if I have the relationship f of x squared, right? And I take the derivative of it, what do I have? I have 2x, okay? The relationship as it extends into the gradient space is going to be the projection of something like a higher dimensionality vector, the transpose of that high dimensionality vector, times that specific point. Argument here. If we have a vector, that's our data vector, right? And we have a target, that's our target at the end of the system. If I want to correlate the relationship of the significance of individual elements, I want to create the mapping function between the input features and the output system, then what I'm going to do is I'm going to take the transpose of this vector times the output, right, and determine whether or not that relationship is being satisfied by the mapping function f. The better that mapping function f, i.e. the network we're utilizing, the closer the correlate between the map function and the output. As I said previously, if I want to update f and I want to make changes to f based upon however many dimensions of weights or significant correlates between the two, then I'm going to utilize the gradient. I'm going to calculate the gradient, okay? Or calculate a matrix version of this gradient, which we call the Hessian matrix, all right? And the vector product times the singularin, the decomposition of the gradient, is the Jacobian, if we're going to borrow those from our previous calculation. So we're going to calculate Jacobian, and then we're going to calculate the Hessian, which is the matrix format of the gradient J of the gradient F, okay? So we're taking the change in the change of error, and we're establishing an update methodology. I know this is where it's starting to, I feel like I'm starting to lose you guys a little bit in some of these areas, so let's stick with this. So as the parameter gets updated and optimized, I'm changing the weight. What happens to the error surface? I'm traveling down the error surface. How much am I changing the weight and in what direction? Either positive or negative. Am I increasing or am I decreasing the slope?
Decreasing.
So I'm increasing The slope here?
Yeah, increasing the slope.
No, I'm decreasing the
You're
slope
decreasing
because
the slope.
it's going up, right? It's getting flat, okay?
Yeah, yeah, it's
Yeah.
getting flat.
What's also happened to the gradient? Gradient is also getting flatter. Initially, the gradient is showing us that if I were to be moving and increasing the slope, what would happen? I would be going back up, right? So I'm actually, initially here, I'm saying that the slope of this surface relationship is creating a relationship of an error, which is the difference between the summation of this and the desired output, right? So MSE is going to be minimized when the difference between the parameter and the data model is optimized, right? Has been reduced to the minimum relative to the gradient surface. So I'm effectively taking the derivative of the derivative in this case. It's a second derivative characteristic, and that is called the Hesse matrix. We'll calculate that in a bit, all right? I'm gonna hop back over to my other slides here. Log likelihood estimators, right? Talk about bias variance lemma. Okay, I'm gonna go forward a little bit. So mathematical modeling, right? We have some ideal characteristic of f of x relative to noise. And we're going to make a creation of a system such that the surface is going to be described by what? The square error in the system. So if I say J then is the square error of the system, J is actually the surface characteristic, or is the projected space of the error. So the gradient of J is the relative instantaneous change to the maximum degree of increase of error relative to that specific surface. It is described by or written as a decomposition within supervised space as grad, if you guys have seen the symbol beforehand, right? It's an inverted delta. And notice this is a vectorized format. Vectorized format. What does that actually indicate? That the relationship between x and y, right? So this function f takes in x and y, and it returns local grad, right, as a vector with magnitude, direction, and relative components for each of the individual independent portions, such that it is the partial of f with respect to x times the component in the ith direction plus the partial of x with respect to y in the jth direction, or the decomposition. So this says how much and in which direction each of the individual components need to move as I decompose that vector into its components in both x and y, or I and j as they decompose in the vector space. Now I'm talking about how we change the values. I showed you this one earlier because this is the version. There's a version of the update slide, the slope slide, right? This one says that if I go against the error of the direction of gradient surface, that currently I have some value of the weight at position k. This means, what is the weight right now? What is the rate right now? I want to know what the weight would be in some position k plus 1. Let's do this with Bayes again, all right? This is the prior, right? This is the prior, right? And this is the posterior. So if I'm saying that I'm utilizing a metric or external evidentiary information to say the evidence is the gradient of J that proves that if I adjust W, that this is the adjusted version of W, right? The next time step. So this is a time step designation as well. We call the difference between the time step designations epochs within neural network space, right? Anybody ever seen that term, an epoch? It's just how long the training cycle takes, right? So one training cycle has to go through the entirety of the data set, or at least the training set that's involved with it, and then return the estimated mean square error value of all the values in the training set. So it's going to go through all the examples in the training set, and then it's going to do what? It's going to take the mean square error of all the values in the training set, the difference between those points, and the letter expectation, and then it's going to update the current value of the weight based upon the gradient of the error surface. So it's saying I'm going to add in the gradient of the error, right, for that particular time step. This is that local maximization function. I'm going to scale it by a small amount. Why don't I just add it all in there? Imagine if every time you did something, right, and you just throw out, you just like, I'm just going to add all this new information, right? All the new information. Example here is you invest in something, right? And you lose some money on that investment. The idea would be sell it all off, right? Just sell the whole thing. Just liquidate your whole portfolio. No, you're going to say, well, I lost this much on this investment, right? I might want to sell that investment and reinvest over here. You're going to take a small amount. Maybe you don't sell all your stock in that thing, right? Or you don't put all of your eggs in that one basket anymore. The relationship here is the scaling factor keeps us from learning from a bad experience. Okay, anybody ever heard that? I know some of you don't drink, but those of you who drink, right? Everybody has a story about somebody with tequila, right? I am never touching that again. I had one bad experience with it. I got so sick, never again in my life, okay? That's when this number is really big, okay? One singular example, one point in time, right, informed by the results of that particular output, says the correlation between tequila and me feeling awful was very high. So what do? I never do it again. I update the weight to just all of that experience is going to change. It's going to erase all previous experience with it, right? Everything that you had beforehand is going to be erased by that one bad experience. The reason why we have to create a learning rate is because we have to place the appropriate amount of significance on one specific bad example in order to be able to determine how that example can inform our future outputs. You change your golf swing a tiny amount, right? Only tiny amount. You don't want to completely change your golf swing. You don't want to go buy new clubs, new balls, new tees, completely change your physical configuration every single time, right? Why? Because if you do, what happens? You're jumping all over that gradient surface. You're jumping around. You're changing the values too much at any given time to make any reasonable assumptions. We note typically that gradient surfaces or the error surface should be continuous and relatively smooth. And in general, right, we're searching this space without fully knowing what's in it. That's another consideration. We've been dropped into the woods. You can't see every bit of the forest, or excuse me, every bit of the geography of the space. You can only see the trees. So from the ground level, you've got fog around us. That's the way I like to talk about the gradient. The gradient is like searching through an area in the fog. You can only see a few feet in front of you. You can see your local area. You see around you, right? You can assess what way is best to go based upon what you can see, but the fog blocks the remainder of the information from you. So all you can do is take a step, right? Step in a direction. If you're walking around in the dark, do you go like this, right? No, you don't make big changes whenever you're walking around in the dark. When you're uncertain what lies in that direction, you take small steps, okay? This is the step rate, how big the steps are allowed to be, and it is based upon what? A scaling factor of the degree to which and the intensity of which the gradient changes in that direction. Notice what I'm doing to the weight with it. What am I doing to the weight? I'm subtracting this from the weight. Why? What is this? Positive rate of error. It is always the greatest direction of error. So if it is pointing in the greatest direction of error, it's effectively saying if you increase the weight by this much, you will be increasing you will get the maximum return on investment for being more wrong. The gradient actually tells us which way is up on that surface, which way is increasing that value j. So the grad of j will always be the direction of maximum increase of the function j. If error surface is created by the mean square error of the system, then the gradient j is the amount and the direction in which to change the values of j to result in the greatest increase in relative error. So if it's the amount and direction to change the increase of error, right, all I have to do is go in the opposite of whichever way is going to be considered the maximum increase of error, and what I'm going to do. That is the maximum decrease in error. Relative to that relationship, if I say go in exactly 180 degrees in the opposite direction of the cliff, right, you should be going backwards towards safe land. That would be the relationship. That's the idea. Now, what happens when I change this? I update this, I add it to new WK at the location, right? And then the new WK location should correspond to some vectorization of the relationship of the input vector x times the error estimation k, which is the error estimated at that local point k for the surface, times that learning rate. Learning rate update parameters are going to say that relative to the number of free parameters in the system, I have to calculate the j, right, the error surface for all relative weights. So that vector of weights, w, is going to have a calculated set of j. J becomes what then? A matrix for the error calculations. The gradient of j becomes calculation of maximum increase value for that value j. And so there is also a matrix created for that system. So all I have to do is calculate a matrix calculation in matrix form for this system in order to get the outputs. I know it's...
Wow.
Okay, be quiet, it's fine. Don't complain. No, this is fun, right? Everybody loves math. I'm messing with you guys. One of the things to always do. What is one of the things to always do when you're looking at an equation like this? No, there's a bunch of equal signs. No, I mean this. Because that means you're just saying the same thing a different way.
Yeah, okay. Yes.
That's it. That's all I mean. So stop looking at the whole thing as if it's all one whole thing you have to understand, and say it's just saying the same thing in a different way each time again. So over there on the left-hand side, I say j n plus 1 on relationship to the error relative to that time step plus 1. That also correlates to j of n plus grad of the weights for j for n times what? Delta w of n. So now we have grad and delta. What is that w? Vectorized version of the weights.
Yeah.
Vectorized version of the weights. So if I say take the current value of the gradient times the current structure of the weights, right, and generate the update for the error system based upon your understanding of the current error surface, then the relationship for the value assignment such that over here on this far side, what do we have? We have the update level times the weights of the gradient of j of n times j of n weights the gradient. Well, that's the same thing twice, right? No, because look, it's got that new in there. It's got that learning rate, right? So it's the learning rate times the relative change in the gradient itself. This is saying how much are we updating it relative to the magnitude of the vector itself. How much of the vector are we actually utilizing? Because it is a scaling factor. So I say the relationship of the likely change in error, right? This is the change in error. The relationship of the likely change in error at the next step is related to the current error minus however much I decide to update it relative to however much total error was assumed at that point. This is obvious. This is obvious to it, right? How much with a return on investment, how much we reduced from this, right, to this should be proportional to however much we decided that we were going to include the error estimate in that previous step. So if I say 40% of your error was established based upon your value for the first weight of 2. So you say, well, I'm only going to use a small fraction of that. I'm only going to use 1% of it. Okay? So I'm only going to use 4%. I'm only going to adjust the current weight by 4%, either positive or negative, depending on which value that particular gradient was pointed in, right? I'm gonna either add or take away 4% of that value. My hope would be then what? I should create a resultant reduction of error proportional to the 4% of the estimated gradient times the 40% that was estimated in the previous gradient assessment, right, the ratio there, relative to the original error in the system. And if you don't, right, if you don't get at your next step of the process an improvement in error relative to that previous assessment, what's happened? Something changed, right? Something changed. This says that for a multivariate expansion of the system, we should have a return on investment relative to the amount of the gradient we're integrating. This is effectively how much we're learning from each epoch. Each time we go through the data set, how much information about that iteration through the data set are we learning? How much specific change within our internal connections are we making based upon that output? This is the idea I was describing previously. One bad example can ruin your whole experience in life for some specific event, right? Eat bad fish, eat bad shrimp, whatever, and you want to stay away from it for the rest of your life because you felt so terrible as a result of it. So you take too much from that specific example and modify your weights, modify your likelihood to eat fish in the future, right? This is me extrapolating it out to the example that we had previously. I say, how bad was that experience, right? Well, how much am I going to take that experience relative to every other time I've done the same thing, right? I've ate fish every day for most of my life, and then I have one bad day of fish, and it's terrible. It's a really bad day, right? You're in the bathroom all day kind of situation. You say, well, I'm only going to make a small caveat, right? I'm not going to eat that kind of fish perhaps in the future. So, what was the impact of that event, of that experience, relative to your likelihood to change the relationship in fish? How is that update to your system likely to change or result in you avoiding getting sick in the future? That's what this equation is, right? Your likelihood or your relative error distinction between good, bad experience learned by how much weight or how much significance you place upon examples, a set of specific examples within the system, such that you change your affinity for specific behaviors relative to a desired outcome in that case, right? Sorry, we're out of time for today. I went over a little bit. But learning, if learning is nothing more than changing our patterns of behavior based upon the experiences we have, we now have the equipment to be able to tell us how to change those values such that we can update to be able to provide more desirable results within our personal experience, change our behaviors in order to create the desired outcome in that system. We'll continue on with the math as we go on into Thursday. Thank you.